This is Unit 10, Section 2, Theoretical Probability. First part is just theoretical probability. So example, a random number is chosen from numbers 1 through 20. Find each probability and write your answer as a simplified fraction. Okay, before we do the problems, let's do the notes real quick. Stuff you need to know. Theoretical probability is just how likely something will happen if you have perfect circumstances, like a perfect situation. So in a perfect world, theoretical is how likely it could happen, as long as everything is completely even and all that stuff. Okay, that's perfect circumstances. The formula for probability for anything, you would have probability of some event, okay, whatever it is you're trying to find the probability of. It would equal the outcomes that you want. So again, it depends on what you're looking for. So that's what you want to find, divided by what's called a sample space. Okay. Now the sample space is just all outcomes that are possible for one thing. So pretty much you have the outcomes you are looking for your event on top, and all outcomes that are possible on the bottom. You divide those, simplify the fraction, and that's your probability. Okay? So let's look at number one. We have the probability of, a random number is chosen. So this first question, what this means is I want the probability that I choose a 4. Okay? I'm picking numbers 1 through 20, or from those numbers. Okay? So let's look at my formula. So my probability of my event is 4. So equals the outcomes that you want. Well, if I want 4, there's only one possible 4 that I could get, right? Because between 1 and 20, there's only one number 4. So the outcomes that I want, there's only one of those, divided by the sample space, which is the total possible outcomes. Well, if I'm picking between 1 through 20, that would be 20 numbers, right? And I can't reduce that, so that's my answer. So if I randomly choose a number between 1 and 20, the probability of getting a 4 is 1 out of 20, because there's only one 4 out of the 20 numbers. Hopefully that makes sense. If not, maybe the next one will help. Okay, now I want probability of an even number. Okay, well again, I'm looking at numbers 1 through 20. So if we have even and odd are the only two possible choices, half of those should be even, right? Okay, so the outcomes that I want, if I want even numbers, the total number of even numbers between 1 and 20 would be half of that, which is 10. Okay, so I have 10 even numbers between 1 and 20, and my sample space, the total for all the total possible outcomes for everything, is 20 numbers again. Okay, so I'm only doing 20 numbers. So 10 over 20, I can reduce this, and this would just be half. So the probability of getting an even number between 1 and 20 is half, because half are even, half are odd. That makes sense, right? Okay, next one. Prime numbers. Okay, so I want the probability that I randomly pick a prime number between 1 and 20. If you don't remember, prime numbers are only divided by themselves in 1. 1 is not counted in that. So let's go ahead and, if you need to, list the prime numbers. So I'll list them right here. So prime, we have 2, 3, 5, 7, 11, 13, 17, and 19. Those are the only ones between 1 and 20. Okay, so I want the outcomes that I want. So I want prime numbers. How many do I have? Well, we just count those. So I got 1, 2, 3, 4, 5, 6, 7, 8. So I have 8 prime numbers divided by my sample space. So my total possible outcomes, I'm still using 20 numbers, and I can reduce that. I can divide each by 4. You'd get 2 and 5. So the probability of getting a prime number between 1 and 20 is 2/5, or 2 out of 5. Okay. So that's basic theoretical probability. All right, moving down, simple probability. Simple just means it's one event happening at a time. I'm going to use the same formula for theoretical, the probability of event, the one we just did above, right here. So I'm using the same formula, but simple just means it's only one event. So I'm only doing one thing at a time. Okay, and of course these are going to be word problems. So I want to find the probability and write as a simplified fraction. So all your answers for this should be a fraction of some kind. So 4 says you choose a random letter from the alphabet. What is the probability you choose a vowel? Okay, so I want probability of vowel. Okay, so now I need the outcomes that I want. So I want vowels. How many vowels are there in the alphabet? Well, there's A, E, I, O, U. So there's 5. So I have 5 vowels, and my sample space, my total possible outcomes, if I'm pulling letters from the alphabet, there are 26 letters in the alphabet, and I cannot reduce that, so that would actually be my answer, 5 out of 26. There are 5 vowels out of 26 letters, so that's my probability that I would pick a vowel. Number 5, you pick a random card from a standard deck. What is the probability you did not pick a diamond? Okay, so if I don't want to pick something, that's called a complement. So if you want to write something down for here, so complement is probability of not happening. Okay, that's all that means. So sometimes it'll ask, like with number 4, what's the probability of doing something? That's just normal. But when it says, probability of not doing something, we call that the complement. And the complement just means probability of not happening. Alright, so you need to know some things about a standard card deck if you don't already. There are 52 cards total. There are 4 suits. There's a hearts, diamond, spade, club. Numbers go from 2 to 10. Then you have jack, queen, king. Those are considered face cards. And then you have ace. Okay, so if you don't know much about card decks, you probably want to go look those up and just write some things down as far as what they have of each. Okay, so I pick a random card from a deck. What's the probability I did not pick a diamond? Okay, well, if there are 4 suits in a card deck and there's 52 cards total, that means there's 13 of each suit. That'd be ace 2 through 10. That's 10 cards, plus the jack, queen, king, that's 13. Okay, so if I don't want to pick a diamond, I'm going to take my total, and I'm going to subtract all the diamonds in the deck. So there's 13 of each suit. So if it said not heart or not spade or whatever, it's 13 of each one. So I subtract those, and you get 39. That means there are 39 cards that are not diamonds. So when I do this, I want probability of not diamond. So if you want to write the P of not diamond, remember that from logic. That symbol means not. Okay. So the probability of not getting a diamond, I have 39 cards that are not diamond. Out of my sample space is 52 because I have 52 total cards in a deck. And I can actually reduce that. 13 goes into those. So if I reduce that, 13 goes into 39 3 times, 13 goes into 52 4 times, and that would be my answer, 3/4. So the probability of not a diamond is 39 out of 52, or reduce would be 3 out of 4. Okay? So that's all that is. Okay, so that was simple, and now we're going to have compound. So compound just simply means I have more than one event happening together, or like one after the other kind of thing. Okay, so there's some things with compound probability that you need to know before we even look at the problems. So we have what's called AND events, and then we have OR events. So AND events, this would be like probability of something, some event A and some event B. So if it says what's the probability of doing this and this, that's an AND event, and you multiply the two fractions, or however many you have. I'm pretty sure I only stuck with 2 at a time just to make it easy. So here, if it says AND, you multiply fractions. Okay, that's AND events. My second kind that I have is called OR events. So I can say, what's the probability of this or this happening? So it's probability of some event A or some event B. Okay, and again, we kind of went over this with logic, the and or kind of thing. So and they happen together, or as long as one of them happens. So if I do or, I'm going to add the fractions. Okay. So those are my two compound events, the types that I have. So I'm either going to multiply or I'm going to add. Those are the only two things I can do. Okay, so find each compound probability and write your answer as a simplified fraction. And again, sticking with fractions, I don't want decimals. Okay, 6. You roll a die, then choose a random card from a standard deck. Okay, first off, you got to know there's 6 sides to a die. Everyone says dice. Dice is more than one. So a die is just a single one. So there's 6 sides to a die. And a random card, we just went over, there's 52 cards in a deck. So it depends on what it's asking. So what is the probability you roll an even number? So we have even number, and that's our keyword. Then draw a black card, because in cards you have hearts and diamonds are red, spades and clubs are black. Okay. So the first one, so I roll a die. So I want an even number. Okay, if I want to write, if you want to write the P, we can do that. So probability of, we'll just do even and black. Okay. And because I'm doing and, I'm going to multiply. That's our keyword there. Okay, so when I multiply these, well, let's write them out first. So even number. So if I have a die that's 6 sides, 1 through 6, how many even numbers are there? Well, there's 2, 4, 6. So that'd be 3 even numbers. And we said there are 6 total sides on a die. And so we multiply. And then black cards. Well, if there's half the deck is red, half the deck is black, that would be out of 52 cards, that's 26 out of 52. Okay. Now, of course, with anything with fractions, I've always said that you should always reduce. That makes it a lot easier. So 3 out of 6, we can reduce that to 1/2. And then, of course, 26 out of 52, we already said was half, right? So when we multiply these, we multiply the top numbers. 1 times 1 is just 1. And the bottom numbers, 2 times 2 is 4. I can't reduce that, so that would be my final answer. So the probability of rolling an even number and drawing a black card would be 1 out of 4. So I mean, it's a good chance, but it's not high. So the chances of both of those happening, you have a better chance of it not happening. And if you have a die and a deck of cards at home, you could try these things out and see what happens. But theoretically, like perfect conditions, it'd be 1 out of 4. So if you did this 4 times, one of them, this would happen, the other 3, this would not. That's not saying it would actually come out that way, but that's what theoretical is. Okay, 7. You roll a die, then choose a random card from a deck. What's the probability you don't roll an even number, or draw a black card? Okay, well, if I don't roll an even, then I'm rolling an odd, okay? So I have P of not even, or draw a black card. Okay, so not even, well, if I'm not even, I'm odd. And on a die, 1 through 6, I have 1, 3, 5. So I still have 3 out of 6. Okay. And plus, because we have or, so it's plus. I'm adding. Or draw a black card. Okay, well, we just did that. So half the deck is red, half the deck is black. So we still have 26 out of 52. Now remember, when you add fractions, the bottom numbers, the denominator, has to be the same. Okay, well, if I reduce these 1/2, reduce that to 1/2. I will say they don't always reduce quite that nicely. Sometimes one fraction may need to get bigger and the other fraction may need to get smaller to be the same. It just depends on the numbers. Okay, so now I can add though. So if I add 1/2 plus 1/2, I get 2 halves, which reduces to 1. So theoretically, given perfect conditions, if I were to try this, this means that 2 out of 2 or 1, so 100% chance this would happen every time. Now, realistically, that probably would not happen every single time, but again, this is theoretical. This is based on perfect conditions. So given perfect conditions, in theory, that scenario should always happen every single time. It probably won't realistically, but you know, that's what it is. Okay, last part, independent and dependent events. Okay, so there is a difference. Independent, I guess we can write these down just so you have them. Okay, so we have independent events. I don't know why it keeps changing colors on me. So we have independent. That just means that first outcome, so whatever our first outcome is has no effect on the second. So that it has nothing to do with the second outcome. Okay, so that's independent. The first outcome has no effect on the second outcome. So no matter what happens first, and that does look kind of weird, doesn't it? It'll let me erase. I'll redo it. So like so some examples of independent events, like okay, if you, I don't know, say you cook a meal and then you go watch TV. Well, whatever meal you cook has nothing to do with what you're going to watch on TV. If you pick, let's say you call a friend, like you call a random friend on your phone, you know, and then you randomly pick a drink out of the fridge. Those have nothing to do with each other. The first one, who you call, has nothing to do with what drink you're going to pull out of the fridge. So just things like that, things that are just not related at all. If you did the first one, it would have no issue or no bearing or no anything on the second one. That's independent. The second one, of course, would be dependent, and that's where the first one does affect the second one. So we have first outcome does affect, we'll put it that way, second outcome. Okay, so dependent. So that one's like, let's say you pick a random state to go visit, and then you pick a famous landmark to go see, well, the state you pick would determine or would have some effect on what landmarks you can go see in that state, right? Okay, that'd be an example of one. Picking like a random restaurant to go to and then picking something off the menu, well, the restaurant you picked on the first decision would affect your second one of what you're eating. Okay, things like that. So things that are directly affect the next thing that happens, that's dependent. All right, so let's see how this plays out with some word problems. The example, I have a bag of 5 green marbles. I have 7 red marbles, and I have 3 blue marbles. Okay, I want to find the probability and write my answer as a simplified fraction. Okay. So what is number 8? What is the probability you choose a green marble, put it back, and then choose a red marble? Okay, then we have the and. So I want to choose a green marble, then I put it back, and then I choose a red marble. Okay, this would be an independent event because I pick out one marble on the first one, right? I see what color it is, but because I put it back, that means the second time that I draw a marble out of this bag, it's like I started over. So whatever I picked the first time has nothing to do or does not change the results or anything of the second one, because it's like I'm restarting every time. Okay, that would be independent. So because it's independent, it works out a different way. And then number 9, you'll see that the dependent's different. Okay, so number 8, probability that I choose a green marble. Okay, well, if we want to do, okay, probability of green and red. Okay, now there's no really way to write independent versus dependent. You just write it like this. You just have to know if it's which one it is. Okay, so I choose a green. So probability of green, well, the total number of possible green marbles that I could pick from, I have 5. So I have 5 green marbles divided by the total, my sample space. Well, I add up all the marbles, that'd be 7 plus 3 is 10, plus 5 is 15. Okay, so I have 15 total marbles. So that's my chance of getting a green. And means multiply. Now, because I put this back, my sample space is the exact same as the first one. So I know my sample space, my bottom number, doesn't change because I put the marble back after the first one. So it's like I started over. Now I want to choose a red marble. Well, it says I have 7 red marbles. Okay, now I can multiply those, but first I would reduce. So 5 and 15 would be 1 and 3. I can't reduce 7 and 15, which is fine. I don't need to. So I can just multiply across. So 1 times 7 is 7. 3 times 15 is 45. That does not reduce, so that is my final answer. Okay, so the probability that I choose a green, put it back, and then choose a red is 7 out of 45 times. So if I did this 45 times, 7 of them should be this scenario. Everything else should be different. Theoretically, that's what that is. Okay, last one, number 9. What is the probability that I choose a green marble, keep it out, so now I'm not going to put the marble back, and then choose a red? Okay. So again, I use the same colors, I just changed the word just to show the difference between the two. This would be dependent because if I pull out a marble and say it's green or whatever, but I keep it out, I don't put it back in. That means the second time when I go to draw the next one, my sample space, my total number of marbles in there have changed. So my first outcome does affect the next one. That's dependent. Okay, so I'm going to have probability of green, I don't know why I did a comma, and red. Okay, so it starts off, it looks the same starting out. You just have to know dependent or independent. Okay, so this one's dependent. So here's how this works. I'm going to do the first one like normal. So green marbles, I have 5 green marbles, and there's still 15 marbles in the bag. And means multiply. Okay, but because I kept it out, I'm going to choose a red marble, so I have 7 this time. But my sample space, my total possible outcomes, if I took a marble out on the first one and I didn't put it back and I had 15, so I had 15, I take one out, and then it stays out completely. And then I go to draw the second one. Instead of having 15 marbles, I now have only 14 because I took one out and I didn't put it back in there. So that's how dependent and independent are different. Dependent, if you're doing the same, hopefully you're doing the same thing, your sample space should decrease as you keep going. If I kept doing this, say I choose a red, keep it out, then choose a green, keep it out, then choose a blue, keep it out, my sample space every time will go down. Independent, it will always be the same, it won't change. Okay, so now I just have to multiply these, but I'm going to reduce. So 5 and 15 is 1 and 3. And now, hey, I can reduce 7 and 14. That gives me 1 and 2. So look at that. I can multiply on the top. 1 times 1 is 1. On the bottom, 3 times 2 is 6. And that's it. Can't reduce that at all. Okay, so that is dependent, independent, that's the difference. So independent, my sample space should never change. Dependent, it should go down each time, depending on what I'm doing. Okay, and that's it for the notes.